Hello students, I am Dr. Rajaram Dhok from Savitribai Phule Pune University affiliated Agricultural Development Trust Shardabai Pawar Mahila College Shardanagar Baramati. Let's start. Ionic Solids Lecture 9 Defects in Crystal Structures. In the defects in crystal structure, we see that firstly the different types of compounds observed in the crystal structure. So there are mainly two types of compounds. One is stoichiometric compounds and other is non-stoichiometric compound. So what is stoichiometric compound? So when number of positive and negative ions are exactly same in the ratio as shown by their chemical formula, that is called as stoichiometric compound. Means in this stoichiometric compound ratio of positive ion and negative ion is exactly same, and there is example of NaCl, CHCl. Then second type, that is non-stoichiometric compound. In this compound, ratio of positive and negative ions are different from that indicated by the ideal chemical formula. So in that stoichiometric compound, there is observed defect, and that is called as stoichiometric defect. So we see what is the stoichiometric defect. Generally, the perfect crystals not shows any defects. So perfect crystal means the crystals in which definite arrangement of ions at absolute zero temperature is observed. There is not any disturbances, there is not any defects. But as the temperature increases, some vacancies are created in that crystal. Means in the crystal at higher temperature, some ions lose their original position and occupy some other places. This is known as defects in the structure. So this type of irregularities occur mainly in stoichiometric compounds. So depending upon which ions lose their positions, that stoichiometric defects are classified into two types, that is Schottky defect and Frenkel defect. So what are that Schottky defect or how they are obtained? What is Frenkel defects? We see in detail with the help of certain diagrams. So firstly with the Schottky defect. So this Schottky defect is formed in stoichiometric compounds, and this defect is observed due to the equal vacancies or holes at the lattice sites in the same crystal. Means there are equal number of missing positive and negative ions in the crystal lattice, and due to this crystal remains neutral. So we say that in NaCl, here same number of Na ion and Cl ions lose their positions, and when same number of positive and negative ions are lost, then there is not any effect of charge on that crystal. So such type of Schottky defects are mainly observed in the compounds. They have very small difference in the size of positive ion and negative ion. So radius ratio, that is radius of cation to radius of anion, is nearly equal to 1 in that compounds. So there are some examples, that is NaCl, KCl, CHCl. It shows such type of defects. So such Schottky defects that is found strongly in ionic compounds and which have high coordination number. That is the example is NaCl. So in this, energy required to create such type of defect is very small. And so by the absorbance of small energy, such type of defects are observed. You see this diagram. In this diagram, here we have drawn cations are attached by anion, anions are surrounded by cation, cation, anion, cation, anion. So this is the sequence. Now you see there are some positions of cation and anion, they are vacant. So you see this is the cation position. So one cation leave their positions from this crystal lattice and one anion leave their positions from the crystal lattice. So from this crystal, one cation and one anion lose their positions and there is formation of defect that is called as Schottky defect. The other example we take that four cations and four anions lose their positions. So that is also the Schottky defect. So simply we say that Schottky defect means same number of positive ions and negative ions lose their positions and there is formation of vacancies. Second defect, that is Frenkel defects. So this Frenkel defect is also observed in stoichiometric compounds and this defect is due to the dislocation of ions in the lattice. Usually positive ions lose their position and it occupy the interstitial positions because these positive ions or cations are smaller in size as compared with anions, and this smaller size cation leave their positions and it occupies some other space in the same crystal. In between the ions there are some space and in that space that ions or cations occupy the space. So generally such type of Frenkel defects is observed when there is large difference in the size of positive and negative ions. So generally it is found in the compounds when negative ions are larger and positive ions are smaller. So radius of cation to anion, it is sufficiently less than 1. So examples in which this Frenkel defect observed is AgBr, silver bromide, because in that silver bromide Br is larger size anion and Ag is smaller size cation, and such smaller size cation Ag leaves their position and it occupies some other place in the same crystal. So such type of defects are observed in the compounds which are highly coherent characters. It is found in the compounds that is having low coordination number, and the different examples in which such type of Frenkel defect observed is AgCl, AgBr, AgI, ZNS, and energy required to create such type of defect is large as compared with Schottky defect. Now you see this structure. You see this is the crystal lattice, and in that crystal lattice there are cation, anion, anion, cation. They are arranged with each other in all the three dimensionals. We have shown here only the two-dimensional structure, but you see here the vacancies. Here this cation leave their position from this their original position and it occupies some interstitial position. And so here anion not loses their position, only cation lose their position, and that is the Frenkel defect. Now I drawn here both the diagram on the one page for your simplification. You see Schottky defect in that one cation and one anion or same number of cation and anion leave their positions and that crystal shows neutral charge. In the Frenkel defect, only cation lose their positions and it occupies interstitial position and it not loses or leaves from the total crystal or out of the crystal. So charge on that is also remains same. So this is the difference between Schottky defect and Frenkel defect. Now, what is the effect of this Schottky and Frenkel defect on the different properties of that ionic solid? So different properties of ionic solid is changed due to the formation of such type of Schottky and Frenkel defect. And in that, the first property or that can affect is low density. So when there is defects, then such type of structure have low density because certain space is observed in between the ions, and because of that density of such type of ionic solid becomes less. Then electrical conductivity. So electrical conductivity is one of the important phenomena in ionic solid. So when such defects are observed, then crystal becomes weak conductor of electricity because there is some space, and because of that space there is disturbances in the movement of electron from one point to other point, and such type of crystals not shows proper electrical conductivity, and that electrical conductivity decreases when there is defects in the crystal structure. Then third effect observed on the stability of crystal. So number of folds when more in numbers, or when there is large number of folds, then at that time there is lattice energy is less, and when that lattice energy is less, then stability of that crystal structure is less. One of the other property is dielectric constant. So the values increases due to the repulsion between the like charged ions. So here, when positively charged ions or some ions lose their positions, and in case of that Frenkel defect, when positive ion lose their positions, then the negative ions or anions are in contact with each other. And when anions are in contact with each other, then dielectric constant value increases because there is more repulsion between the charged ions or same type of ions. Now we see the other point, that is solubility of ionic substance in water. So ionic substances are soluble in water, and solubility of that ionic solid depends on the lattice energy of that ionic solid and solvation energy of the ionic solid. We know that water is a polar solvent, and due to the presence of partially positive and partially negative charges on the ionic solids, that ionic solids are soluble in water because water have also partially positive charge on the hydrogen and partially negative charge on the oxygen. And when in that water such type of ionic solids are dissolved, then it dissolves easily, but it depends upon the lattice energy and solvation energy of that ionic solid. We take here example of NaCl. So this is the NaCl crystal. In that NaCl crystal, the Na is surrounded by Cl and Cl is surrounded by Na. Now, when such type of NaCl crystal is added in the water, and we take the large amount of water, and in that when that NaCl is added, then how that solvation process is carried out, or interaction of that water and NaCl is carried out. So in the water, the oxygen is negatively charged. So that negatively charged oxygen attracts positively charged sodium. In some other water molecules, positively charged hydrogen attracts negatively charged chlorine. So in this way, here negatively charged oxygen attracts positively charged Na, and positively charged hydrogen of the water molecule attracts negatively charged Cl. So in this way, Na and Cl, they are attracted in the opposite direction, and there is breaking of bond between Na and Cl. So that is shown simply here. You see here, Na is surrounded by large number of water molecules. So one Na is surrounded here by 4 water molecules, and again the other ion, which is chlorine, which is bonded with Na, they are surrounded by also the 4 water molecules. So you see here Cl is surrounded by here 4 hydrogen of the 4 water molecules, and in this way Na and Cl are attracted in the opposite direction by that water molecule, and here interaction of Na plus ion and Cl minus ions with water molecule is breaked, and there is formation of dissociation of NaCl in that water molecule, and that NaCl undergoes dissolution, or there is formation of solution. So that all is carried out, or such type of process is carried out in all ionic solids. Now we see here hydration of Na plus ion. How that actual hydration carried out? So you consider again same example, and that is the same concept. Na plus ions pen surrounded by water molecule, then that 4 water molecules attracts that Na. Again that every water molecule is again attracted by other water molecule. That water molecule attracted by other water molecule. In this way, there is formation of first hydration sphere, second hydration spheres, and in that first hydration sphere, second hydration sphere, large number of water molecules present, and it attracts Na plus. That same case is observed in the Cl minus ions, and because of that, NaCl or any ionic solid undergoes dissolution, and there is formation of solution, and such type of process that is called as solvation of ionic solid.